Okay, so today we're going to look at natural logs. And what we're going to look at is a natural log. We talked about this briefly before you got started with all of this. The natural log is part of the exponent of the base e, log base e. So we know that log base e of x is equal to the natural log of x. So we use this so much in science and math applications that we just give it its own little thing. And its own little thing is ln for natural log. Don't know why it's backwards. It's probably due to the Latin. But it's ln of x is equal to the log base e of x. So e is Euler's number, which you will remember we talked about when we were doing continuous compounded growth. It's 2.71856, blah, blah, blah. It's the equivalent of a number like pi. It's irrational, so it doesn't repeat, it doesn't terminate, but it is a constant. And it's something that we can use to predict growth in a constant growth environment or continuous growth environment, or growth or decay. A lot of times when we do growth studies in science, this is the number that we'll use. So I want you to apply the rules. But I said, right, Ms. Rivera said you only had 5 rules to use. So the thing is that the rules are the same for a natural log as they are for a log. Okay? Look how this works out. 5 times the natural log of e minus the natural log of 5 becomes the natural log of 2 to the 5th. There's our exponent, or our power property, divided by 5. There's our division property. Exactly the same thing. You're just using the ln button that's right under your log button on the calculator. So the natural log of 36 minus the natural log of 4 is the natural log of 36 over 4. It's the natural log of 9. Boom. That's it. 1/2 the natural log of x minus 4 times the natural log of y. We use our property, our power property, and then we use our division property, just like we use for regular logarithms, okay? So I want you to take a few minutes as we go through this and get used to seeing that sometimes you will use the natural log. As you do physics and chemistry and biology, a lot of times they have the natural log function. So what about natural log equations? You're just going to use e to the x. If e to the x is equal to 16, we take the natural log of both sides, becomes x ln e, right? The natural log of e is equal to 1. Remember that is log base e of e. So over here on the left, you see I have the log base e of e is equal to x. E to the x is equal to e to the 1. So x is equal to 1. So that kind of makes some of these a little bit easier. So the ln of e is equal to 1, you just drop it. The natural log of 16 is a constant. You enter it into your calculator, you push enter, and you get 2.773. If I have the natural log of e to the 2x minus 3 is equal to 1. I get rid of the 6, move it to the other side. I take the natural log of both sides. My exponent becomes my coefficient. The natural log of e is equal to 1. And look how simply this will solve. Simple, simple, simple. Just using those rules that we learned at the beginning of the chapter. Here I have 2 plus e to the x minus 1 is equal to 2. And again, when we subtract, remember how we ended up with e to the x minus 1 equals 0? There is no number that I can raise this to make it equal 0. I can get really close, but it doesn't happen. Here we're going to look at using the natural log We have the natural log of 2x is equal to 4. I rewrite it because we use exponents to solve logs. I rewrite it as e to the 4th is equal to 2x. I calculate e to the 4th on my calculator. I get 54.598 is equal to 2x. I have 27.3 is equal to x. Again here, 2 times the natural log of x minus the natural log of 2 is equal to 6. I use my power property. I use my quotient rule. I rewrite it as a single logarithm, a single natural log. And then I solve it. So take a minute and look through the steps and notice that it's just basic. Once you get it into that exponential form, that exponential equation, you're just solving. One last problem. This is a solution to the word problem that you have. I didn't write it down. Notice that this is a compounded growth question. And it says that it has... Okay, so this is the question where you have 25% of something left, right? It's talking about carbon dating, so you have 25% left, and it wants to know what's going to be the number of years. In this case, and this is something to think about as you use and do your examples, in this case I use 1 for the amount that started, and 0.25 for how much I have left. Because this rate is constant, it's going even if I had 10 grams of something, I would still have 2.5 left at the end of this time. So I can use 1 because I started with 100% and I finished with 0.25 or 25%. So to me, this makes the equation a lot easier. Notice the first thing that I did is I took the natural log of both sides. I brought my exponent down to be my coefficient. I divided and I solved for t. And so we find that theoretically, it's taken 11,552.45 years to reach only 25% remaining of the material. Okay, so this is your final section for the chapter. You're going to do your Math Excel assignment, and then you're going to do your daily check, and then I want you to start working on the natural log handout and the review packet that I left. Again, if you need to talk to me, you can always do Plus Portal. You can email me. You can try me on Remind. If we need to Skype or FaceTime, I can do that. But you just need to let me know. And remember that I am 6 hours ahead of you. So if you want to Skype at 7 o'clock, that's not really going to work because it's going to be 1 a.m. where I am. So if you need any help, I'll be glad to help you. You just have to reach out to me.